Hello, everyone. Welcome to the 42nd meeting of Introductions and Group Theory and Triangulated Categories. Today, our speaker is Serge Bouc from Université de Picardie, Jules Verne, and he'll be speaking to us about functorial equivalence of blocks.
Okay, so first of all, I'd like to thank you, Rudradip, for the invitation to give this talk here. It's a great pleasure and also a great honor. The first thing maybe I should say is that is apologize to specialists of triangulated categories because there won't be essentially any mention of that in this talk. I will stick to the group theory part of the name of this seminar. So I will speak about this notion of functorial equivalence of blocks. And this is a recent joint work with Deniz Yilmaz. And I will start by recalling some probably very boring elementary facts on categories. After that, I will introduce a category we're interested in. And then the functors on these categories will be the functor of interest, and it will give rise to this notion of functorial equivalence of blocks. So let me start with very elementary generalities on categories. A category, of course, consists of objects and morphisms. This notion was introduced by Eilenberg and MacLean around 1945, say. But it has been quickly observed, in particular by Grothendieck, that the objects of the category don't matter so much. And there are several arguments to that. First of all, one can reformulate the axioms of category theory using only the notion of morphisms, and one recovers objects from the identity morphism, which can be characterized among the class of morphisms. The second argument is that there are equivalent categories, so essentially the same category from our point of view, which may have completely different objects. And there is a famous example that I could maybe develop at the end of this talk if you're interested. And on the contrary, there are some mathematical notions may appear equipped with a natural notion of morphisms. For example, groups. Groups would be equipped with group homomorphism as morphisms. But this notion is not always the only possible one, nor the best one. Depending on the aspect of the objects you're interested in, you may use one notion of morphism or another one. So the general, say, philosophy, to use a big word behind that, is that in some cases, it may be interesting to change the morphisms. I will give a list of examples of that which have appeared in the past decades. Say one of them is the category of finite groups, where, of course, we don't consider group homomorphism as morphism, but the morphisms we consider are induced by bisets, that is, sets induced with two actions of group which commute. And looking at representations of this category leads to the notion of biset functors, which have been an interesting tool to solve, in particular, some open problems in the representation theory of finite groups. The second example I would like to give, which I like very much, is even simpler, the category of finite sets, but where morphisms from one set to another are not given by maps or applications, but by correspondences. So here, correspondence is subset of a direct product of two sets. And this is a joint work with Jacques Thévenin. We started this more than 10 years ago now. And the origin of that is that we were tired of bumping into really difficult question in the theory of biset functors. And we wanted to have a somehow simpler framework where possibly we could develop easily what we wanted to develop. So this gives rise to the theory of correspondence functors, and we have quite a number of papers on that. And there are lots of very interesting and very nice structure showing up when you look at these correspondence functor, in particular posets or lattices or things like that. There is yet another example, which is the category of rings. And again, I will change the morphism. And this category of rings, I will consider morphism given by bimodules. So it's very similar to what we did with bisets and groups. And the composition of morphism is given by tensoring bimodule. And this point of view is interesting if you're interested in particular in studying not the internal structure of rings, but rather the categories of modules. In particular, it's a very natural framework to study Morita theory of R modules or some rings. It also has been used in particular by Marcus Linkelmann to define some transfers in Hochschild cohomology or Hochschild homology induced by a specific type of bimodules. And so this enters this particular framework. I will finish this list by several other examples on which I know essentially nothing, so please forgive me. But I thought they would be interesting to mention. The first one is the category of motifs in algebraic geometry, where the objects of the category are say, schemes over some commutative ring, but morphisms are constructed from high-level intersection theory and higher Chow groups and this kind of stuff, on which I essentially know nothing once again. Another example is theory of bordisms or co-bordisms in algebraic topology, where objects are varieties of a fixed dimension n, but morphisms are given by varieties of dimension n+1. And looking at some type of representation of this category leads to so-called topological quantum field theories, which are really important in modern theoretical physics in particular. And of course, there are lots of other examples like categories of fractions, categories of spans, quotient categories, localization, derived categories, and so on. So at least I will have mentioned one type of triangulated category in this talk. So from now, I will stick to finite groups. And of course, there is an obvious category of finite group, as I said before. The obvious candidates are the group homomorphisms. And if you consider this category, then you immediately get the notion of a simple group. What is a simple group? So G is a finite group, and G is simple in those terms if and only if any group homomorphism, any morphism in that category, from G to another group, either is trivial, which means that F actually factors through the trivial group, or F is injective, which means that actually it is a monomorphism in the category. Very good. So we have these simple groups, and we may view these simple groups as the atoms of categories similar to chemistry, and we may want to describe all finite groups, using these particular type of atoms. And of course, so being given a finite group, can we decompose that into these atoms? And of course, it is a celebrated Jordan-Hölder theorem, which tells us precisely that for a given finite group, there is always a composition series, and the successive quotients in this series are well-defined finite simple groups. Okay, now the question, of course, is can we describe the finite simple groups, or can we describe the atoms of this theory? Do we have a kind of periodic table of these elements in that case? And the answer today is yes. But as you know, it has been a very hard task to classify all the finite simple groups. This is sometimes called the huge theorem. And even if the proof has been simplified quite a lot, it's still very complicated and intricate. So that's the first point. Another point I would like to mention is also similar to chemistry, is that in chemistry, you may have different molecules with exactly the same atoms, but one of them is a medicine and the other one can be toxic. And the situation here is quite similar, even if I don't know any toxic finite group. But what happens is that, of course, you can have two different finite groups, meaning two non-isomorphic finite groups with the same atoms, that is the same composition factors. And this is related to the classification of extensions of finite groups, which in general is in itself a rather difficult problem. So we have this perfectly respectable category of finite groups with very lots of nice results. And however, it's also a bit complicated because of that. And we may try to compare it with a very elementary category that every first-year student knows very well, which is the category of finite dimensional vector spaces over a field, okay? And in that category, we also have the notion of simple objects and of composition series, but the situation is much nicer. There is only one simple K vector space, which is K itself, of course, up to isomorphism. And any finite dimensional vector space is entirely determined by the length of any of its composition series, which usually we call the dimension of the vector space. So we have these two types two kind of extreme types of categories, one of which is of interest to at least to group theorists, and the other one which is very convenient because we can apply methods of linear algebra for vector spaces. And so we would like to try to mix those two ingredients and get a category of finite groups where we can use some kind of linear algebra. And this is what we try to do now. And the first idea, of course, is to use group algebras for that. So throughout now, we fix a field K, which we assume algebraically closed and of characteristic P, which may be zero for a short while, but as usual in this domain, the interesting case is when P is positive. So we have, for a finite group G, we have the group algebra KG, which is a vector space with basis G and multiplication given by a linear extension of the multiplication in G. And we have a corresponding category of finitely generated module or finite dimensional KG module, which is the same thing. And here the notation is standard. This lowercase m means finite dimensional or finitely generated. And an uppercase m would mean the category of all KG modules. Okay, so one can consider first this category, and the theory is well known since the n of the 19th century due to work of Frobenius in particular. When P does not divide the order of G, as you know, the category of Kg module is semi-simple, meaning that any Kg module is the direct sum of simple ones. There is only a finite number of such simple Kg modules, and they are characterized by their character. So this goes back to Frobenius, and I'm always amazed that Frobenius invented the theory of characters for finite group without knowing group representations or Kg modules for finite group G. Everything he knew was the group algebra over the complex numbers. And the problem he was interested in was to find the irreducible factors of the group determinant. So he exchanges letters with Dedekind in particular at the time. And he managed to build this complete theory of characters for finite group only to solve this problem. And he solved this problem. And some years later, he invented also the group representations. So this is an amazing work. Now, of course, if P divides the order of G, then you also know that by Maschke theorem, this is no longer true, meaning that there are non-simple indecomposable Kg modules, so modules you cannot split in non-trivial direct sums, but which are not simple, that is, they admit non-trivial proper submodules. Maybe what is less well known is that in general, there are infinitely many such indecomposable modules up to isomorphism. And more than this, this infinity is very infinite. That is a problem of classifying all the indecomposable Kg module for an arbitrary finite group G is a wild problem, meaning that there is essentially no hope to come to a classification of these modules. So let me come back to the group algebra. What can be said in general is that we can try to split this algebra as a direct product of indecomposable K algebra, algebras that cannot be split as a direct product, non-trivially. And these are called the blocks of Kg, or the block algebras of G over K. And they are all two-sided ideal, of course, of Kg, of the form Kgb, where B is a primitive idempotent of the center of Kg. So these B's are called the block idempotents. For that, there is a well-defined unique list, finite list of that. And any of these block algebras is of this form Kgb for a block idempotent. I need to introduce one notion related to block or block idempotence, which is the following. For block idempotent B of Kg, we choose a minimal subgroup D of G such that there exists an element C in Kg, which is invariant by conjugation by D. This is a notation with this exponent here, such that B is equal to the sum of the conjugates GCG minus 1 for G in a set of representative of D cosets in G. So this may seem a little strange, but it's really important. And one can show that such a minimal subgroup exists because the group D equal G has this property. There is an element B, so C equals B in that case, such that B is equal to B, and B is indeed invariant by conjugation by G, because B is in the center of Kg. So there is such a minimal subgroup, and such a minimal subgroup is called a defect group of the group B. One can show that it is a P group, and also that if we have two of these, actually they are conjugate inside the group G. So it's essentially unique up to conjugation by G. So sometimes I will probably say the defect group of B, which is a bit incorrect, of course, because in general there are several different subgroups. Right. So let me come back to my aim. My aim is to build a category of finite groups with different type or other type of morphism. And so the first idea would be to come back to this group algebra and use bimodules. So possibly a morphism from G to H would be simply KH, KG bimodule. Like I just recalled, there is a theory of category of rings, and morphisms are given by bimodules. And first, I observe that a bimodule for two-group algebra is the same thing as a module for the Cartesian products of the groups. This is only a change of notation, actually. It's a usual trick in group theory that a right action of an element G is actually a left action of its inverse. So these notions of bimodules and modules for product group are the same, actually. And it means, in particular, that any notion that makes sense for modules over finite groups also makes sense for bimodules. And now, okay, we could consider the category where objects are finite groups and morphisms are isomorphism classes of bimodules, and composition is given by tensoring bimodules, etc. The problem is, as I said before, there are just too many modules for finite groups. And in particular, there are too many bimodules for finite groups also. So it's probably not a good idea to build a category where we have no hope to say anything interesting on the morphisms. So the idea is now to restrict to more specific classes of bimodules. So we are looking for specific classes of modules over finite groups, and the first idea is to consider permutation KG module. So what is that? It's a KG module which admits a basis, a K basis, which is globally permuted by the group G. And that's a very nice notion. We would like, in addition, that the modules we consider, or the bimodules we consider, be closed under taking direct summands. This is why we consider a more general notion, which is the notion of a p-permutation KG module. So there are different terminologies for that in the literature. They are also called trivial source KG modules, and even sometimes permutation projective KG modules. All this is the same notion. I'll stick to this p-permutation terminology in that talk, except for one notation where I'll use the T of trivial source at some point. So I just said that a p-permutation KG module is a direct summand of a permutation KG module. It need not be itself a permutation module, but one can characterize these guys by saying that a KG module is a p-permutation module if and only if its restriction to a CeLO p subgroup of G is a permutation module. Okay, so it means it's a module, a KG module, which admits a basis which is invariant by the action of a given CeLO p subgroup. And of course, this condition does not depend on the chosen CeLO subgroup. It also means that if G itself is a p group, then a p-permutation KG module is simply a permutation module. Okay. So we have this. Now let me give the important result in that domain, in that there are finitely many indecomposable p-permutation KG modules up to isomorphism. This goes back to a paper by Brouet in 1985, where it parameterizes with indecomposable p-permutation KG modules in a very nice way and gives lots of information on that. Some examples, there are some examples that you all know. For example, you take a projective KG module then a projective KG module is a direct summand of a free KG module, and a free KG module is obviously a permutation KG module. For example, KG has a basis G, which is invariant by the action of G. A slightly more general case or example is, suppose you start with a projective module for a factor group G mod n of G, where n is some normal subgroup of G, and you inflate that module, that is, you consider it as a KG module where n acts trivially. Then in general, the module you obtain for KG is no longer projective, but it's still a p-permutation KG module. And the last procedure I would like to mention to produce p-permutation KG modules from known ones is induction. So you start with a p-permutation module for some subgroup H of G, and you induce it to G. And the three procedures give you essentially all the p-permutation KG modules for a given finite group G. You start with a projective module for a subquotient of G. You inflate it to a subgroup of G, and then you induce to the whole group G. Okay. As I said before, notion which makes sense for modules also makes sense for bimodules. So there is a notion of p-permutation bimodule, exactly in the same way. And an important example is KG again. So KG is a KG-KG bimodule for obvious reasons. And it's a permutation module because G is invariant by left and right multiplication. Another remark to make here is that if we restrict this bimodule either to the left or to the right, we get a free KG module, in particular, a projective KG module. A slightly more general case is when we have a central idempotent of KG, and we consider KGB. So this is again a bimodule because B is central in KG. And it's a direct summand of KG as KG bimodule because B is an idempotent. So in particular, KGB is a p-permutation bimodule. Moreover, if we now restrict the action either to the left or to the right, then we see that KGB is a direct summand of the free module KG, and in particular, it is projective. This motivates the following definition, say, for finite group G and H, a diagonal p-permutation KH-KG bimodule is a p-permutation bimodule, which is projective as a left KH module and as a right KG module. You may wonder about this terminology diagonal. It comes from the fact that an indecomposable such module is actually a direct summand of a module induced from a twisted diagonal subgroup of G. So to draw a picture of this situation, we have two groups, G and H, and you can view these as coordinate axes in the direct product. And a diagonal subgroup is something which is like this, which does not admit any horizontal part nor any vertical part in its graph. So it's just a picture, of course. Okay, so we have this notion of diagonal p-permutation KH-KG bimodule that we use intensively in what follows. Now, suppose we have three finite groups G, H, and K. We can consider such a bimodule M for H and G, and such a bimodule N for K and H, and try to tensor them over KH. And one can show easily that this tensor product is again a diagonal p-permutation module for K and G, bimodule for K and G. So if we look at what is written on the slides, we have two important things, the last point and the first one. Because the last one tells us that perhaps we could have a composition in some category using these bimodules. And the first one tells us that we can have an identity endomorphism of G using KG, which is indeed an identity for this tensor product over KG. And this is what we will do now. So we come to the notion of a diagonal p-permutation functor. Again, this is a joint work with Deniz Yilmaz. So first we fix a ring of coefficients, a commutative ring with identity. And for finite group G and H, we denote by RT delta of H and G. So it's a short. For the free R module with basis, the set of isomorphism classes of indecomposable diagonal p-permutation KH, KG bimodules. So it's really a short. And here the delta stands for diagonal. And T is everything which remains from this trivial source terminology I mentioned some minutes ago. Okay, so if we have now two finite groups like this and an arbitrary diagonal p-permutation KH, KG bimodule, we can split that as a direct sum of indecomposable ones, and it gives us a corresponding element of that group or that modules that we denote with brackets, square brackets around M. Okay, now we have for three finite group G, H, and K, there is a well-defined bilinear map from RT delta of KH cross RT delta of HG to RT delta of KG, which is induced by this tensor product of bimodules. And now we have the definition of a category. So this category is denoted by RPPK delta. So delta is again for diagonal. K is to remind of the field K, and R is our ring, and PP is for p-permutation here. Now the objects of this category are the finite groups, and the home set from G to H in that category is this module RT delta of H and G. And you will observe immediately that we switch the variables, which is very convenient when working with these bilinear maps that we will use as a composition in that category. So this is the composition in this category. And the identity morphism of the object G is KG between brackets. So we have seen that KG is a diagonal p-permutation KG, KG bimodule. So it's an element of that group. And it acts indeed as an identity element for this tensor product or the composition in this category. Now we get a perfectly respectable category, and it's moreover an R-linear category because the home sets are in a natural way R modules, and this structure of modules is actually bilinear. Composition is actually bilinear for this structure, either on the left. And this is an R-linear category, and now we consider these diagonal p-permutation functors over R, and they are just R-linear functors from this category to the category of all R modules. For some general arguments of category theory, these functors, together with natural transformation between them, form an abelian category that we denote with this curly F symbol and lots of decoration. But probably at some point I will write simply F for that category. So these are these diagonal p-permutation functors we consider. And the first result and main result we obtain is the following. In the case where the ring R is an algebraically closed field of characteristic 0, then this category of functors over F is a semi-simple category, meaning that any such functor is the direct sum of simple ones in particular. And this raises the question of the description of these simple functors. And for this, I need some terminology and notation. What we call a D delta pair, LU, consists of a finite P group L, so a group of order power of P, and a P prime automorphism U of L acting faithfully on L. So P prime means of order prime to P, and acting faithfully meaning that the subgroup generated by the group generated by U is actually a subgroup of the automorphism group of L. So this is the delta pair. And when we have such a pair of a group and an automorphism of this group, we can build a semi-direct product, denoted in this way. And this leads to the notion of isomorphism of such pairs. So an isomorphism of the delta pairs LU and MV is actually a group isomorphism from LU to MV, which in addition sends U to a conjugate of V. When the two pairs are the same, we get an automorphism group of the pair LU. And obviously, this group contains the group of inner automorphism of the semi-direct product LU, and the quotient is the group of outer automorphism of LU, which we denote by out of LU. With this notation, we get the following results. So the simple diagonal p-permutation functors over F up to isomorphism are parameterized by isomorphism classes of triples LU, V, where LU is such a D delta pair, and V is a simple module for this outer automorphism group of LU over the field F. In other words, it's simply an irreducible character of this group. And this gives a notation, of course. The simple functor parameterized by the triple LUV is denoted by S sub LUV. Actually, we have more than this. We can, for example, describe the evaluations of such functors at an arbitrary finite group. I can tell you more about this at the end of this talk if you're interested.
Could I interrupt? Could I ask a question,
yes.
Please, Serge? You started off with characteristic 0 at the top. At the bottom theorem, do you have characteristic 0, or is that restriction no longer there?
Yeah, no, it's the same F, that at the top.
It's characteristic 0 in the bottom theorem.
Yeah,
also.
and algebraically closed also, yes.
Yes,
yeah.
Okay, thank you.
But this is, of course, this is the field of coefficients. It has nothing to do with the field K, lowercase k, that we consider from the beginning. The field K of characteristic P, which is always of characteristic P. And here it's assumed to be positive. So we have one field of characteristic P for P permutation modules. And we have this category, which is R linear for a ring R. And in that case of this theorem, and we consider R to be a field of characteristic 0, right? I hope this answers.
Thanks, yeah.
Okay. Okay, so let me come back to blocks. And suppose we have a finite group G and a central idempotent of Kg. Then we can consider KGB. We have seen that this is a diagonal p-permutation bimodule. So it's an endomorphism of the group G in that category we introduced. More than this, if we now take the tensor square of that bimodule, it's really easy to see that we get KGB again. So it means that this endomorphism of G in that category is actually an idempotent endomorphism of G in that category. Even more, if we now start with orthogonal central idempotence of Kg, meaning that their product is equal to 0, then for the same reason as before, the tensor product of the corresponding bimodules is equal to 0. And it means that the corresponding idempotent endomorphism of G we obtain are also orthogonal. And now we can make the list of the block idempotents of Kg, which are the primitive idempotents in the center. And we get a decomposition of Kg, which is the identity endomorphism of G in that category, as a sum of orthogonal idempotents in the endomorphism algebra of G in that category. And what is interesting, of course, is that even if the block idempotents are primitive in the center of Kg, they are no longer primitive in general in the endomorphism algebra of the group G in that category. And this is what we will see in a short while. So there are also natural functors associated to these blocks, which are direct summands of representable functors. So if we have such a pair, again, we can consider the functor that we denote by RT delta sub GB, which is obtained by precomposing the representable functor on the right with this idempotent. That is, it maps a group H to RT delta of HG composed with this idempotent KGB. In other words, it is a set of morphism from G to H in the category, which factor through this idempotent, or again, equivalently, which are invariant by right composition with this idempotent. There is a special case of that when B is equal to 1, we drop it from the notation. And we think of this functor, which is the representable functor at G, as the group G viewed in this category of functor. This is the usual Yoneda embedding of a category in a category of functor. Okay. Now, this representable functor splits as the direct sum of the functor associated to GB and the functor associated to G1 minus B, because B and 1 minus B are orthogonal. It's the same result as before. And now we have the Yoneda lemma in this R-linear framework, which tells us that the representable functor is always a projective object, because taking Holmes from a representable functor at G to any functor M is just evaluating M at G, and evaluation is always an exact functor in this type of category. So it means in particular that this functor RT delta sub GB is a projective object of this category of functors. Now we can consider the block idempotence of Kg, and we can decompose this representable functor. In other words, the group G viewed in that category of functor as a direct sum of functors associated to the various blocks of Kg. And it gives the idea of trying to compare these functors associated to blocks for possibly different groups and see what happens. Can we say anything interesting in that situation? This leads to the definition. We say that when we have two pairs GB and HC of a finite group and a block idempotent of its group algebra, we say that the pairs GB and HC are functorially equivalent over R if the corresponding functors are isomorphic in the category of functor. Using, again, the Yoneda lemma, it's equivalent to saying that there exists an element sigma in CRT delta of HGB and an element tau in BRT delta of GHC, such that sigma composed with tau is equal to KHC and tau composed with sigma is equal to KGB. Sometimes, in a general categorical situation, one says that the idempotent endomorphism KHC and KGB are conjugate in the category in question. So this is equivalent to requiring that these functors are isomorphic here. Okay, now let me come back to the case where R is this field F of characteristic 0. we have this functor associated to a pair consisting of a finite group and a block of kg. Then we know also that in that case, this category of functors is semi-simple. So it means that this functor associated to the pair GB splits as a direct sum of simple functors SLUV in that category of functor. And the question is how? In other words, can we have an idea of the multiplicity of a given simple functor as a summand of the functor associated to this pair GB? Can we have formulas for that? And actually, we have three different answers for that. One is in terms of some fixed points of some subgroups of out LU on V. The next one is in terms of U invariant GB Brouwer pairs. Don't worry, if you don't know the vocabulary, it's not really important. And the third one is in terms of U invariant local pointed groups P gamma on KGB. So Brouwer pairs were introduced by Alperin and Brouet in 1979. And local pointed groups were introduced by Puch in 1981, I think. Anyway, I won't go into details. I can give you more information on this formula if you're interested. Anyway, these formulas are precise enough to allow us to prove, for example, the following result. It's so a theorem. You suppose we have a block of the group algebra of a finite group G with a defect group D. And then the following are equivalent. First of all, the block B is nilpotent, which seems a bit weird when you're not a specialist, because B is an idempotent, which is also nilpotent. And so it is zero. But this nilpotency notion here refers to a paper by Brouet and Puch in 1980, I think, where they define the sort of nilpotent structure on a block. And of course, which doesn't mean that the block idempotent itself is nilpotent. This is related to a celebrated theorem by Frobenius again. So this is the first assertion in this series of equivalent condition. The second one is that if SLUV appears as a summand of FT delta sub GB, then actually U is equal to 1. The third condition is the same with V replaced by the trivial module. And the last condition is that the functor FT delta GB is isomorphic to the functor FT delta sub D. In other words, the pair GB is functorially equivalent to D1 over F. So this is a nice characterization of nilpotent blocks in those terms. Okay. Now I would like to say a few words on equivalences of blocks, because there are various notions showing up here. First of all, we can try to compare these functorial equivalents when we change the ring R. And it's easy to check using the previous characterization I mentioned, that functorial equivalence over the integers implies functorial equivalence over any commutative ring R, simply because Z is an initial object in the category of commutative rings. So it's really easy to see. There are now in the literature, there are various notions of equivalence of blocks. And this functorial equivalence over the integers is actually the weakest in the following chain. The first one is splendid Ricard equivalence. So this was introduced by Jeremy Ricard in 1996, I think. And if you know these things, you know that this word splendid, according to Ricard, means split endomorphism induced from diagonal. So we recover here this diagonal p-permutation bimodules in this, they are hidden in this terminology, splendid here. So this is Ricard equivalence. Now we have another notion, which is p-permutation equivalence, which was first introduced by Bolge and Su in 2008, and later developed by Bolge and Perepelitsky. There is a preprint, I don't know if it's yet published, in 2020 about these. And finally, the third in this chain is this functorial equivalence over the integers. I could have added functorial equivalence over F, because it's over any ring. Functorial equivalence is weaker than this functorial equivalence over the integers. So you might think, okay, you have a notion of functorial equivalence, but what is it good for? Maybe you have just identified every block of every group with one another, and it tells you nothing. But actually, it's not really the case, because of the following proposition. Suppose we have two functorially equivalent pairs over F. Then one can show that actually B and C have isomorphic defect groups. So the defect group is preserved by this equivalence. And not only that, the algebras KGB and KHC have the same number of simple modules, up to isomorphism, of course. And not only that, they also have the block B and C have the same number of irreducible ordinary characters. So I said nothing about that, but if we have a block idempotent of Kg, there is a way to say when an ordinary irreducible character of G belongs to that block or that idempotent. And this is what this result says. In these two blocks, there is the same number of irreducible ordinary characters.
So excuse me, F is still characteristic 0.
Yes, throughout F as characteristic 0, yes. But here K is not F. Lowercase k is always the field of characteristic P from the beginning, right? Does that answer a question, or isn't?
Yes, yes. Yes, of course. I mean, it's just a bit counterintuitive, right? We would expect the property with K modular properties, and the functorial equivalence is in characteristic 0.
Yeah, it's the point is that as we know the decomposition of these functors associated to blocks, actually well, you have seen that the simple functors are parameterized by triples like this LUV, and what happens is that in the functor parameterized by a block, the largest subgroup L that can occur is precisely the defect of the block. So it means that if the functors are isomorphic, well, the defects are the same, and that's the reason why. But I agree that it's a bit counterintuitive, but that's the way it is. So I would like now to finish with finiteness theorem, which is inspired by an important conjecture in block theory, which is Donovan finiteness conjecture. And it goes as follows. We start by fixing a finite P group D, and the conjecture says that there is only a finite number of equivalence classes of module categories of block algebras over K with defect groups isomorphic to D. In other words, there is up to Morita equivalence, there is a finite number of blocks with defect group D, to be a bit sloppy in the formulation. So unfortunately, we don't prove this conjecture, but we prove a theorem which is inspired by the statement of this conjecture. It goes like this. Suppose D is a finite P group, then there is only a finite number of pairs GB where G is a finite group and B is a block idempotent of Kg, with defect groups isomorphic to D. And of course, there is something missing in that statement, because otherwise we would prove much stronger conjectures than Donovan's. This finite number is only up to functorial equivalence over F. And so it's a way of stating this Donovan's conjecture in the framework of this functorial equivalence. Okay, so that's everything I wanted to tell you. Thank you again for your patience, and thank you again, Roderick, for the invitation.
Thank you very much. Let us all unmute ourselves and yeah, give Serge a round of applause.
Okay, so
If you have any questions, please feel free to ask them now.
oh, sorry.
Could I ask a question?
Yes, sorry, let me, okay. Yes, Peter.
Yeah.
Hi. With this isomorphism of these functors, as you observed, it means you've got some virtual p-permutation modules, I suppose, sigma and tau, I think you called them, so that if you do sigma tau, you get one of these functors, and if you do tau sigma, then you do the other.
Yeah.
I mean, if you've got a virtual permutation module, then there is what one might call an opposite or a dual virtual permutation module, where maybe you take the vector space dual and that's it, and so right modules go to left modules and so forth.
Yeah, precisely. Well, sorry to interrupt.
Yeah, so supposing you require a stronger notion of equivalence. I have no idea, I really don't know, if this may be silly, it might not make sense, but supposing you have a stronger notion of equivalence where your tau is the opposite of sigma necessarily. You require
that's exactly the sorry about this. That's precisely the difference between this functorial equivalence and the p-permutation equivalence. So this p-permutation equivalence, the additional assumption is that precisely tau is the opposite of sigma. But we don't assume that in what we do. We only ask for the functors to be isomorphic. And actually, it turns out that some of the consequences that can be deduced from the p-permutation equivalence can actually be deduced from this weaker form, like the isomorphism of defect groups, and it's enough to assume this weaker version of. But it's very close to the p-permutation equivalence, or this functorial equivalence over the integers, say, is very close to this p-permutation of equivalence. Yes, yeah.
And can I ask also? It's been such a long time, I can't exactly remember if you have a perfect isometry, whether there are some extra conditions, more than just the same number of isomorphism classes of simple modules. So do you get some stronger consequence, perhaps?
That's a very interesting question. Actually, what Deniz observed, actually, it's an example due to Deniz Yilmaz, is that you may have a perfect isometry between blocks without having functorial equivalence. For example, the example is very simple and very nice, due to Deniz once again. You consider the case of where P is 2, and you consider a dihedral group of order 8 and a quaternion group of order 8. And these two groups turn out to have the same character table. And for this, they are obviously perfectly isometric, but still they are not isomorphic, so there is no hope that they may be functorially equivalent, like this, if you believe the theorem I mentioned. that the defect group should be invariant by functorial equivalence. So there is a difference. The question is more tricky, and I'm not sure we have the answer. Maybe Deniz can confirm or not. Is for isotopy between blocks. It's not. It's. I'm not sure of the condition we get with that. So we don't know if isotopy implies functorial equivalence.
I think isotopy implies functorial equivalence over F.
Okay, so you know that, but I don't.
But but we don't know the converse, unfortunately.
Okay. Thanks, Deniz.
Thank you, Peter. Any more questions?
Yeah, could I try to rephrase my concern of before, Serge? You don't happen to have your last slide with the Donovan conjecture? Don't go through. Don't.
I can try to come back, maybe.
No, don't jump through hoops for that. Probably you can do it without writing. So, seen from a distance, there seems to be two notions of equivalence or functorial equivalences here, right? One would be
more than two, actually.
Yeah, but I mean,
it depends on some rings. So,
right. But let's say one of them would be to say that the representation categories of the blocks are equivalent, or
so do you see? Sorry, Paul. Do you see the screen, or?
I do. Thank you very much. So.
Okay.
We could look at module categories of the blocks and ask whether they're equivalent. That is something happening in positive characteristic, right?
I'm not sure I understand. No.
In the Donovan conjecture, this is K linear, K is field of characteristic P.
In Donovan's conjecture, sorry, it's K is a field of positive characteristic P, of course.
Yes, that's what I said. Yeah. Mm-hmm.
Yeah.
So, and you could also ask for derived equivalence and things like that, right? I mean, there are variations.
Yeah, sure. This is what I mentioned with this splendid Ricard equivalence and this
exactly.
Kind of.
But then when you look, so very good. So then you could look at those splendid equivalences and p-permutation equivalence and your version over the integers.
Yeah.
At what stage does it stop to induce an equivalence on the module categories? Because certainly if you pass to F coefficients, with F is in characteristic 0, that category does not induce equivalences, does not induce functors anymore. I'm trying to unpack the pun on functorial. There is a joke, there is something about functorial here, which means two things. One is in this functor category, but another thing it means is that those guys induce functors between module categories on blocks. Or they should.
Precisely, it's not so sure, because already for p-permutation equivalence, you consider some elements which are virtual bimodules, and they are not obviously related to complexes of bimodules. Precisely, that's the difference with Ricard equivalence, and they are just supposed to satisfy some condition, which is an algebraic condition like the one I wrote with this sigma and tau, plus in addition that tau should be the opposite of sigma. So there is not in an obvious way functors. There are not functors associated between the categories of modules to such things. There are morphism between the Grothendieck groups, if you like. But there are no genuine obvious functors induced by such even p-permutation equivalence or by this functorial equivalence, actually.
So even with integral coefficients? Even
with the integral coefficients, yes. Yeah. Because these elements sigma and tau are in general just linear combinations of bimodules. So how can you build a functor between categories of module with a virtual module?
It's because you take a K0 at the given state. I mean, you take this trivial source, you take the isomorphism classes of things, and then you take the formal.
Yeah, sure. That's it. Exactly, yes.
Mhm. Okay,
But
Mr.
I'm sure you can produce something with a two category behind that, and some motivic version of all this. So, I would be glad to see the results. Now, without
Yeah, no,
joking, yeah.
no, you see, because the fact, indeed, if you deal with the K0, there's an alternate sum of things, and it's a bit, it doesn't look like it's concrete. But if you look at K0, since this is a triangulated category conference, the K0 at the level of triangulated categories, any class is the class of an object.
Yeah.
You don't have to make formal differences. And so it seems not completely impossible that there might be an underlying, I see the idempotent more complicated.
It's not completely innocent to take precisely the alternating sum of the terms of a complex, or maybe I'm misleading about triangulated categories, but
that's correct. That's correct.
You lose something when you do that.
Sure. Mm-hmm.
And
Okay,
that's the point. That's why p-permutation equivalence is weaker than Ricard equivalence, for example, because Ricard introduces this complex of this bounded complex of bimodule, which he calls splendid complexes for split endomorphism, etc. And he works with complexes, and it's enough to read the introduction of this paper by he wrote in '96, and that's what he wants to do. He wants to. He says there is something missing in this notion introduced by Brouet of isotopy and perfect isometry and so on. And he says that in this paper he wants to fill a gap by building something in these derived categories precisely, and even in the homotopy category of these blocks. So that's what he does actually.
Thank you.
But what has been considered later, like mainly by Bolge and Xu, Pelitsky and others, is first of all you pass through Grothendieck group, and then you see what happens in there and what can be deduced from this mere assumption that we have inverse element sigma and tau in these groups. So in p-permutation equivalence case, you assume that tau is the opposite of sigma, but we don't. We just consider these functors and use this semi-simplicity theorem in an essential way to produce all these results I mentioned.
Yeah. Are there obvious invariants of the blocks, of the module categories of the blocks that don't pass by that would not be detected by your notion of functorial equivalence?
There are some open questions here. One, open and closed also. One of them is the question of Galois conjugate blocks. So when you have a block of a group algebra Kg, you can look at the action of the Frobenius endomorphism of K, and it permutes the blocks of Kg. So these blocks are called Galois conjugate. It has been considered in particular in work by Rada Kessler. And generally, one thinks, well, specialist of this domain, which I'm not, consider that this Galois conjugacy does not imply a p-permutation equivalent. But Deniz Yilmaz proved that actually Galois conjugate blocks are functorially equivalent. So if this is correct, so this is a work in progress, and if all this is correct, it would prove that p-permutation equivalence is well, at least if this general thought on Galois conjugate block not being p-permutation equivalent, it would prove that there is a genuine difference between p-permutation equivalence and functorial equivalence. So it's only a partial answer to your question, but that's what I was thinking of about this.
Thank you. Thanks.
Thank you, Paul. Any more questions for the speaker?
Just
Could I
following
ask another question? Good.
I was going to ask a short questions. Following up Paul's question, is it true that if two blocks are functorially equivalent, then the corresponding fusion systems are isomorphic? Is such a thing true?
We think we don't know the answer to this question. The point is that this functorial equivalence, I didn't give details on these formulas for functorial equivalence. Maybe I can explain that. So we have several conditions here. We have several formulas. As I said before, for the multiplicity of a given functor, a simple functor in the functor associated to a block. And in one of them, what appears in the second condition is indeed the Brouwer pair, that is the fusion system of the block. But in the formula, we need more than merely the fusion system. We need, in addition, to know for such a pair PE, so such a pair PE, so-called Brouwer pair, consists of a P subgroup of G, and is a block idempotent of K CGP, the centralizer of P. And to know this multiplicity here in the second formula, we must know in addition we must know the group of projective CGP modules. We must know this group, and together with the action of the automorphism group of P on that, or at least the normalizer. So it's not enough to have only the fusion system, but in addition, we must have information on that. And from that point of view, the last formula may be more interesting because we know the multiplicity if we know what Puig called the local category of the block, which involves precisely more information than just the fusion system of the block. So if we know this local category, if we have enough information on that, then we can say if two blocks are equivalent. But there is definitely more information in this local category of Puig than in the fusion system of the block.
Thanks. Thank you.
Precisely because of that, because we in this local category you have in addition, which is somehow hidden, but you have information on the projective on the modules for this block algebra of the centralizer, which you don't get if you just have the fusion system. You don't have information on that, and yeah, that's the main reason.
Thanks.
Thank you, Jürgen.
I don't know how long we've got for questions here. I could keep on asking questions, but should I? Do we have time for questions? Okay, let me ask a question. So so if we deal with bisets instead of the p-permutation bimodules, so if we've got a block, it has a characteristic idempotent.
Yeah.
And can we not also do a similar development with?
That's a very interesting question. Actually,
and then you see where I'm going with this. The bisets are more, in a way, more restrictive.
Sure.
So you get stronger results. If you,
there is definitely a good, that's definitely a good question. What happens is that, well, suppose, let me put it this way. Suppose you have such a pair, GB, and you have a defect group, D of B. Then, of course, you can always consider the functor ft d delta corresponding to, so this is a representable functor ft delta of blank d, and you have this here, this functor represented by gb, so ft delta of blank g and b, and you can try to see what are the homes between these guys. And of course, again, by Yoneda lemma, what you get is something like B ft delta of G and D and its colleague ft delta of D, G, and B. And when you look at that, and if you look at as a source idempotent of the block B, then you can cut actually this ft delta of blank D by some I. And at some point, you get indeed some idempotent in ft delta of D and D. You get some element associated to this whole situation in that. And then that's really interesting because D is a P group, and a p-permutation bimodule for a P group is simply a permutation module. So this is nothing but what is usually called the Burnside ring of D, and with the addition that it should be B-free, that is, you consider only bisets which are free on both sides. And you get some element in here. And we have, say, with Deniz, we have a, not to say a conjecture, but a question that is, we get an idempotent defined throughout this procedure. We get an idempotent in that, and of course we conjecture that this is a source idempotent. The characteristic idempotent of the block B, but it's not that easy because when you say we take a source idempotent of B, it's not well defined. It's only defined up to some conjugacy by something, and all this is not canonical enough. So probably the idempotent we get in here should be conjugate, at least, to some characteristic idempotent. But so far we couldn't prove that. So, but it's a very natural and interesting question, actually.
Yeah, sure. Can I ask another question? So you're dealing with these p-permutation bimodules that are projective on both sides, and you can parameterize the simples. Do you get a decent formula for the values of the simples at different groups? You may recall that for biset functions which are free on both sides, you know, I got a formula in that case. And do you have a corresponding formula?
Yeah, we have a corresponding formula for this evaluation. I will try to show this. I have to go, where should I go? Probably nearest to the end. Yeah, that's it. Okay, so here are the evaluations of the simple functors. Sorry. So for finite group G at the top, we denote by Q sub GP the set of pair PS where P is a P subgroup of G and S is a P prime element in the normalizer. And the group G acts by conjugacy on the set of these pairs, and we denote by bracket a set of representatives of orbits. Now, for PS in that set, we can build a particular D delta pair, which is just obtained by modding out the part of the group generated by S, which act trivially on P. So in formal terms, we denote by P tilde S tilde the pair PC over C, SC over C, where C is the centralizer in the group generated by S of P, the set of elements which act trivially on P. And well, this tilde on P is a bit of the misleading, because actually P tilde is isomorphic to P, and it's just the same, it's just another version of P, if you like. Okay, suppose now that we have a general D delta pair, one can show that if this pair P tilde S tilde is isomorphic to LU, as in the definition I gave, there is a group isomorphism phi from P to L, such that the square that you can see, I hope, on your screen, consisting of PL and phi on the horizontal lines, and the vertical lines are on the left the inner automorphism induced by the element S inside the group on the group P, and on the other side this is just the automorphism U of L, which can be viewed also as an inner automorphism group, an inner automorphism inside the semi-direct product of L with U. So we have, I didn't finish the assertion, so this square is commutative. In particular, if we now have an element which normalizes the pair PS, that is, it normalizes P and it centralizes the element S, we can, using this commutative square, it gives us an element in the automorphism group of LU. And actually, it gives us a group homomorphism from the normalizer of PS to the automorphism group of LU. And in this way, we can view a module for out LU as an NGPS module. And now we get the proposition. Suppose we have D delta pair and V be a simple module for the outer automorphism group. Then for finite group G, the evaluation of the simple functor at G is isomorphic to the direct sum for PS running in this set of representatives of orbits of pairs, for which the pair P tilde S tilde is isomorphic to LU of the fixed points of V under the action of the normalizer of PS. So this is very similar to the formula you obtained, Peter, because of the following reason. If we restrict everything we did with Deniz to the subcategory of P groups, then the p-permutation modules and bimodules just become permutation modules. That is, we can replace the group RT delta by just Burnside groups of modules or bimodules. And this theory actually restricts exactly to the theory of what you called, I think, global Mackey functors or globally defined Mackey functors. I was confused with the exact terminology. So if you restrict what we do to the category of, to the subcategory of P groups, then you get exactly the theory of global Mackey functors for P groups. And the formula we have here is exactly the formula that you proved for the simple functors in that case. So all that.
Thanks, yes. I recognize the features, yes. Global Mackey functors, at that time, I was proposing as a name for functors where the bisets are free on both sides. And
exactly. So
and then globally defined Mackey functors was what at that time I was writing. It's the same thing as biset functors.
Okay.
That was the term that I was using for.
Okay, so
functors.
these global Mackey functors restricted to P groups are exactly the same as what we do restricted to P groups.
Mhm. Thanks.
Thank you, Peter. Any more questions? I had a very stupid question myself, but I mean, Serge, are you fine with the time now? I mean, or do you have to go somewhere?
Yeah, no problem. No.
So the theorem that you stated at the very end, after you stated the Donovan conjecture, there was this theorem which talked about the existence of only finitely many pairs of GB. Can you go back to the very last slide, like the one before? Thank you.
The very last slide. So let me change that. The very last slide.
I think
Because
in your paper, I think it's theorem 10.6.
there are some. So here's
Yeah.
This one.
Yeah. So this finite number. I mean, is that supposed to be? Can it be arbitrarily high? I mean, I know of this work by my former colleague at Manchester, Michael Livesey, who showed something about I think it's called Morita-Frobenius numbers, and they can be arbitrarily high.
Yeah,
But this is not exactly that, but I mean, I can see like a small analogy.
Yeah, that's an interesting question also. Actually, we didn't really think of that. The main point was, well, we had this D, and we wanted to bound the number of possible functors. So, but maybe that if we look carefully at the proof, maybe there's actually in the proof we have a silly bound in terms of D, which is probably not optimal, but it gives you in terms of the number of things you can obtain. Yes.
Yeah, because I looked at the proof very quickly while you were speaking, and there's this NDL quantity that I don't understand very well, but I have to read the paper more carefully to understand it.
Yeah. So you can, and the proof is not optimal from that point of view. We didn't try to have the best possible bound. The only thing was that there was a bound, and then there were only a finite number of possible functors. So
Okay. Thank you. Any more questions? Anyone? I can see a few messages in the chat from Ergun and Paul saying they had to leave, and they thanked you for the wonderful talk.
Okay, thank you.
Well, if there are no more questions, let us thank the speaker again for this very informative talk. And since his co-author is here as well, let us thank both of them for this very inspiring work.
Thank you for invitation, and thank you for listening, of course. Yeah, thank you.
Okay, I'll stop recording now.